Hello everyone. Today's topic is power amplifiers, class A, class B. My name is Chichanpuri, Assistant Professor, EC Department, Asansol College. So let's start with power amplifier. But first of all, let us see what is an amplifier. So an amplifier is an electronic device used to increase the magnitude of voltage or current power of an input signal. Okay. Used to convert used to increase the magnitude of voltage or current or power of an input signal. Okay, so it takes in a weak electrical signal or waveform, okay, and reproduces a similar stronger waveform at the output by using an external power source. So that's what an amplifier. It will take a weak signal and convert it into a stronger signal. Depending on the changes it makes to the input signal, amplifiers are broadly classified into current, voltage, and power amplifiers. In this article, rather in this lecture, we will learn about power amplifier in detail. So you see the power amplifier. A power amplifier is an electronic amplifier designed to increase the magnitude of power of a given input signal. Okay. The power of the input signal is increased to a level high enough to drive loads of output devices like speaker, headphones, RF transmitter, etc. Unlike voltage or current amplifier, a power amplifier is designed to drive load directly and is used as a final block in the amplifier chain. The input signal to a power amplifier needs to be above a certain threshold. So instead of directly passing the raw audio or RF signal to the power amplifier, it is first pre-amplified using current or voltage amplifier and is sent as input to the power amplifier after making necessary modifications. As you can see here, this is a block diagram of an audio amplifier. Okay. In this case, a microphone is used as an input source. Okay. So this is the input source. The magnitude of signal from the microphone is not enough for the power amplifier. So first it is pre-amplified. Whereas the voltage and currents are increased slightly. When the signal is passed through tone and volume control circuit, we make acoustic adjustment to the audio waveform. Finally, the signal is passed to the power amplifier. Okay, as you can see here, this is the final stage. Okay. And the output from power amplifier is fed to speaker. So now the types of power amplifier. So depending on the type of output device that is connected, power amplifiers are divided into the following three types. Okay. So depending on type of output device. Okay. Audio power amplifier. Now this type of power amplifiers are used for increasing the magnitude of power of a weaker audio signal. Okay. Weaker audio signal. That's important for audio power amplifier. The amplifier used in speaker driving circuitries of television, mobile phones, etc. comes under this category, audio power amplifier. The output of an audio power amplifier ranges from a few milliwatt, okay, like headphone amplifier, to thousands of watts, like power amplifier in hi-fi home theater system. Okay, so that's a audio power amplifier. Now coming to radio frequency power amplifier. Wireless transmission, okay. So because we are talking about radio frequency power amplifier. So wireless transmission requires modulated waves to be sent over long distances via air. The signals are transmitted using antennas and the range of transmission depends on the magnitude of power of signals fed to the antenna. For wireless transmission like FM broadcasting, antennas require input signal at thousands of kilowatts power. Here radio frequency power amplifiers are employed to increase the magnitude of power of modulated waves to a level high enough for reaching required transmission distance. Coming to DC power amplifiers. So DC power amplifiers are used to amplify the power of a pulse width modulated signal. Okay. They are used in electronic control system which needs high power signal to drive motors or actuators. They take input from microcontroller systems, increase its power, and fed the amplified signal to DC motor or actuators. Coming to the classes of power amplifiers. So there are multiple ways of designing a power amplifier circuit. The operation and output characteristic of each of the circuit configuration differs from each other. To differentiate the characteristics and behavior of different power amplifier circuits, power amplifier classes are used in which letter symbols are assigned to identify the method of operation. So they are finally broadly classified into two categories. Power amplifier designed to amplify analog signal. Okay. So power amplifiers which are designed to amplify analog signal comes under A, B, AB or C category. Okay. And power amplifier designed to amplify pulse PWM digital signal comes under D, E, F. In our syllabus, we are interested here. Okay. To amplify analog signal. So this is not in our syllabus. The most commonly used power amplifier are the ones that are used in audio amplifier circuits that they come under classes A, B, AB or C. Now coming to class A power amplifier. Now analog waveforms are made of positive high and negative low. In this class of amplifier, the entire input waveform is used in the amplification process. A single transistor is used to amplify both the positive and negative halves of the waveform. Okay. This makes the design simple and makes class A amplifier the most commonly used type of power amplifier. Although this class of power amplifiers are superseded by better designs, they are still popular among the hobbyists. As you can see here, you can see here VCC resistors is there. It is a single transistor. It will take the input waveform and produce high output waveform. So in this class of amplifier, right now we are talking of class A. The active element or the electronic component used for amplifier, which is transistor in this case, okay, is used all the time even if there is no input signal. This generates a lot of heat and reduces the efficiency of class A amplifier to 25%. Okay, in normal configuration and also 50% in a transformer coupled configuration. The conduction angle, the portion of the waveform used for amplification out of 360 degree. For class A amplifier is 360 degree. So the signal distortion level are very less, allowing better high frequency performance. So now coming to class B power amplifier. So class B power amplifier are designed to reduce the efficiency and heating problems which are present in class A amplifier. We had discussed just now that the problems associated with the class A amplifier. Okay. So instead of single transistor, okay, to amplify the entire waveform, this class of amplifier uses two complementary transistors. One transistor amplifies the positive half of the waveform and the other amplifies the negative half of the waveform. So each active device conducts for one half, that is 180 degree. Okay, one half and another is in another half of the waveform, and two of them when combined amplify the entire signal, and this is how it goes. You see here, input waveform for 180 degree, two conduction angle they will make, and finally this is the desired output waveform. The efficiency of class B amplifier is improved a lot over class A amplifier, okay, because of the two transistor design. they can reach a theoretical efficiency of about 75%, which is more, 25 to 50% compared to, class A amplifier. So power amplifier of this class are used in battery operated devices like FM radio and transistor radio. Because of superposition of two halves of the waveform, there exists a small distortion, however, and at the crossover region. To reduce this signal distortion, class AB amplifier designed. Okay, let us discuss class AB power amplifier. So class AB amplifier are a combination of class A and class B amplifiers. This class of amplifiers are designed to reduce the less efficiency problem, okay, of class A amplifier and distortion of signal at crossover region in class B amplifier. You can see here. So this is how it goes. It uses class A, class B, and a modification circuit like this. Okay. So it maintains high frequency response, like in class A amplifier, and a good efficiency, okay, as in class B amplifier. A combination of diodes and resistors are used to provide little bias voltage, which reduces the distortion of waveform near the crossover region. There is a little drop in efficiency, although the efficiency is dropping 60% compared to class B 75% because of this actually. But the frequency response is good compared to, and even the distortion problem is solved, which was there in the previous two class of amplifiers. Now coming to class C amplifier. The design of class C power amplifier allows greater efficiencies, but reduces the linearity or conduction angle, which is under 90 degree. In other words, it sacrifices the quality of amplification, okay, for increasing efficiency. Lesser conduction angle implies greater distortion, and so this class of amplifiers are not suited for audio amplification. They are used in high frequency oscillators and amplification of radio frequency signals. Class C amplifiers generally contain a tune load which filters and amplifies input signals of certain frequency, and the waveforms of other frequency are suppressed. As you can see here, this is a typical, it's a tune load, okay, this tank circuit is there, and in this way it produces the. So in this type of power amplifier, the active element conducts only when the input voltage is above a certain threshold, which reduces power and increases efficiency. Now power amplifier applications. Let us talk of that. Below the applications of power amplifier across different sectors. Consumer electronics. So audio power amplifiers are used in almost all consumer electronics, ranging from microwave oven, headphone drivers, televisions, mobile phones, and home theater systems to theatrical and concert reinforcement system. Now industrial application is there. So switching type power amplifiers are used for controlling most of the industrial actuator systems like servos and DC motors. Wireless communication, it finds application. High power amplifiers are important in transmission of cellular or FM broadcasting signal to users. So high power level made possible because of power amplifier increases data transfer rates and usability. They are also used in satellite communication equipment. Now power and efficiency of a class A power amplifier. The fixed bias circuit connection shown in the figure can be used to discuss the main feature of a class A amplifier. As you can see here, is a fixed bias circuit. You can see here EBC, okay, this is the input, and we are taking the output across here, okay, V0, and this is the VCC. The beta of power transistor is generally less than 100. The overall amplifier circuit using power transistor being capable of handling large power or current, not providing much voltage gain. DC bias. The DC bias set by VCC and RB fixes the DC bias current at You see here IB, which is this current, okay, is equal to VCC minus VBE divided by RB. Okay. IC, we know IC is equal to beta IB. Therefore, VC is equal to VCC minus ICRC. To appreciate the importance of the DC bias, the operation of the power amplifier, consider the collector characteristic shown in the figure. You can see here, this is the collector characteristic. Okay, this is in the x-axis there is VCE, and in the y-axis there is IC. Now VCE versus IC, okay, and the graph is obtained. Okay, so this is the transistor characteristic showing load line and question point. A DC load line is drawn using the values of VCC and RC. Okay. The intersection of the DC bias voltage of IB with the DC load line then determines the operating point Q for the circuit. The question point values are those calculated using the equation shown. If the DC bias collector current is set at 1/2, the possible swing of the signal between 0 and, you can see here, from 0 to VCC by RC, the largest current swing will be possible. Okay. Additionally, if the quotient collector emitter voltage is set at 1/2 the supply voltage, the largest voltage swing between 0 to VCC is also possible. So now we will talk of AC operation. When an input AC signal is applied to the amplifier of the figure, you can see here, this is a figure, the output will vary from its DC bias operating voltage and current. A small input signal as shown in the figure will cause the base current to vary above and below the DC bias point, which will then cause the collector current output to vary from the DC bias voltage set as well as the collector emitter voltage to vary around its DC bias value. So power consideration, the input power with no input signal drawn from the supply is, so PI, that is the input DC, is equal to VCC into ICQ, that is the current which we have got at the Q point. As you can see here, this is the Q point which we have got. You can see here, this is the Q point which we have got here. So now this is the region where it operates. Okay. Even with an AC signal applied, the average current drawn from the supply remains the same. So PIDC represents the input power. Output power and efficiency. The output voltage and current varying around the bias point provides AC power to the load. The AC power is delivered to the load RC in the circuit of figure as given by this one. So using RMS value, P0 AC, that is output AC, is equal to VCE RMS, IC RMS. Okay. Output power is equal to, now we can write down IC square RC. Okay. Because we know V is equal to IR. Okay. So as we know, V is equal to IR. So we can write down this expression, and finally we can write down like VC square by RC. Okay. So this is the RMS value. Using peak value, we can get this peak value VCE IC by 2. Again equating, we can get it IC square RC by 2. So finally we get VC square by 2 RC. Okay, this is the peak value. Using peak to peak value, you see, just peak to peak value, what we will get? We will get VC square peak to peak divided by 8 RC. So this is the AC power delivered to the load RC. Now talking of efficiency, the efficiency of an amplifier represents the amount of AC power delivered. It is transferred from the DC source. The efficiency of the amplifier is calculated using, you can see here, percentage efficiency, output power by input power. Output power is AC, input power is DC into 100%. Okay, so finally we can equate this, and we will get percentage efficiency is equal to VC square peak to peak by 8 RC, which we have got from here, into VCC ICQ into 100%. Now talking the maximum efficiency. So maximum efficiency we can get maximum efficiency is equal to maximum power output AC by maximum input DC into 100%. Okay. So we equate the values with what we have got in the previous slide, and eventually we get the maximum efficiency to be 25% nearly. The maximum efficiency of a class A amplifier is thus seen to be 25%. Now let us talk of class B amplifier. As you can see here, so this is a diagram for a push-pull operation. So class B operation is provided when the DC bias transistor bias just off, the transistor turning on when the AC signal is applied. This is essentially no bias and the transistor conducts current for only one half of the signal cycle. To obtain output for the full cycle of signal, it is necessary to use two transistors and have each conducts on opposite cycles. As you can see here, it conducts for the opposite cycles. Okay, the combined operation providing a full cycle of output signal. Since one part of the circuit pushes the signal high during one half cycle, and other part pulls the signal other part pulls the signal low during the other half cycle, this circuit is referred to as push-pull circuit. Okay, so in objective questions MCQ, it comes in university. Okay, so regarding push-pull amplifier, you need to always go for class B amplifier. Okay, so class B amplifier is actually a push-pull circuit because of the operation in which it does. Now the arrangement of a push-pull circuit is shown in the figure. Now we will talk of the circuit. You can see here. So this is the arrangement. Just two transistors. Okay, fine, we'll explain. When the signal on transistor Q1 is positive, the signal on Q2 is negative. You can see here, plus minus, by an equal amount. Okay. During the first half cycle of operation, transistor Q1 is driven into conduction, whereas transistor Q2 is driven off. The current I1 through the transformer results in the first half cycle of signal to the load. During the second half cycle of operation, reverse happens. Transistor Q2 now is driven into conduction, whereas transistor Q1 is driven off. The current I2 through the transformer results in the second half cycle of the signal at the load. So first, second. So in this way, the overall signal develops across the load, then varies over the full cycle of signal operation. Now let us talk about the advantages of push-pull system. Push-pull circuit gives more output per active device. That means, because no even harmonics are present in the output of a push-pull amplifier, such a circuit will give more output per active device for the given amount of distortion. For the same reason, a push-pull arrangement may be used to obtain less distortion for a given power output per transistor. Eliminates any tendency towards core saturation and non-linear distortion of the transformer. The DC components of the collector current oppose each other magnetically in a transformer core. This eliminates any tendency towards core saturation and consequent non-linear distortion that may arise from the curvature of the transformer magnetizing curve. Ripple voltage will not appear in the load. So the effect of ripple voltages that may be contained in the power supply because of inadequate filtering will be balanced out. Now this cancellation results because the current produced by this ripple voltage are in opposite directions with the transformer winding and so will not appear in the load. Now we will compare advantages of class B as compared with class A. It is possible to obtain better power output, the efficiency is higher, and there is negligible power loss at no signal. Now the disadvantages of class B compared to class A operation, the harmonic distortion is higher, self bias cannot be used, and supply voltage must have good regulation. Now we will talk of the input power. The power supplied to the load by an amplifier is drawn from the power supply which provides the input or DC power. The amount of this power can be calculated using, you can see here, this is the expression for the input DC, VCC IDC. In class B operation, the current drawn from a single power supply has the same form of the full wave rectified signal. Okay. So IDC is equal to 2 by pi IP. And if you put, it will be VCC 2 by pi IP. Put in this place, IDC. So output power, the output across the load is given by, you can see here, RMS by load resistance. So if you get, it will be VL square peak to peak divided by 8RL, okay? Because this is nothing but, if you talk of peak to peak, it will be V by 2. So 2 by 2 square is 4, it will come down, then it will be 8 here. So this is the expression. Now we will talk of the efficiency. The efficiency of the class B amplifier can be calculated using the basic equation, this. You can see here, similarly like other like previous amplifier, percentage efficiency is equal to output power by input power, and output power is obviously AC, input power is DC into 100%. Okay. So just we have found out this output power in the previous slide. We will just equate this all, and we will get eventually the maximum efficiency. Equation above shows that the larger the peak value, the higher the circuit efficiency. Okay, you can see here, because it depends on VLP. Okay, of the maximum value, when this maximum efficiency, then mean this one. So as you can see here, so maximum efficiency or other percentage efficiency is 78.5% in case of class B amplifier, which is good compared to others. The maximum efficiency of class B amplifier is thus seen to be 78.5%. Now coming to class C amplifier. With class B, we need to use a push-pull arrangement. That's why almost all class B amplifier are push-pull amplifier. With class C, we need to use a resonant circuit for the load. This is why almost all class C amplifier are tuned amplifier. Again MCQ question. With class C operation, the collector current flows for less than half a cycle. A parallel resonant circuit can filter the pulses of collector current and produces a pure sine wave of output voltage. The main application of class C amplifier is with tuned RF amplifier. Okay, so it's again MCQ question. The maximum efficiency of a tuned class amplifier is 100%. So if you see here, this is the figure of a class C amplifier. Okay, as you can see here, a tuned circuit is here. Okay, the AC input voltage drives the base, and an amplifier output voltage appears at the collector. The amplified and inverted signal, as you can see here, the signal is starting from here, but here this is signal starting from the negative side. So it is actually inverted. Okay, is then capacitively coupled to the load resistance. Because of the parallel resonance circuit, the output voltage is maximum at the resonant frequency. Okay, which is given by FR is equal to 1 by 2 pi root over of LC for this tank circuit. Now on the other side, at the either side of the resonant frequency FR, the voltage gain drops as shown in the figure. Okay, you can see here the voltage gain is dropping like this for at this particular frequency, the frequency of the tank circuit. For this reason, a tuned class C amplifier is always intended to amplify a narrow band of frequencies. This makes it ideal for amplifying, okay, so ideal for amplifying radio and television signal, because each station or channel is assigned a narrow band of frequencies on both sides of the center frequency, because for every channel you will be having a band of frequency. So for one channel, then again next channel with this FR will be changed, but it will be having again a fixed band, a particular band for that particular channel. So it is used as a tuner actually. That's all. Thank you so much for today's lecture.